Okay, so let's get started. The lab. So the post web page, I always post things there, and then the TA, once he sees it, he cross posts it. But I'll tell him to cross post it to them. Yes.
When I tried opening it on the website, it's information denied.
Oh, good. But I will fix that right after class. I usually test, but this time I did not. What happened to this projector? Okay. All right, so we'll fix the permission problem. It should be visible soon. Now, just to finish what we started last time, and we're going to start the very last component of the class, which is on distributed systems. So we last time, just as a recap, we were talking about I/O systems and basically how device drivers work. Okay, so as I said, I/O devices are typically slow, and most I/O devices would have a controller attached to it. The controller is the hardware component that is responsible for processing I/O requests that are being sent to the device. So typically, the way things would work is CPU would issue an I/O request to the device, and then the device would go off and perform that request or execute that request. The controller would execute the request. Right? And there are a couple of ways to implement device driver. The simplest way is polling, where you go and keep checking whether the request that was issued has finished, so that you keep polling, and once it's finished, you take the results and then you issue the next request and so on. This is typically used for the very simplest device drivers. Polling typically involves some busy waiting because device drivers, I/O devices are slow. So the CPU will have to wait for a while in a loop, just polling the device. Okay? But that's the simplest way to write a device driver. The more sophisticated way, or the more traditional way to write a device driver is interrupt based, where you issue a request to the I/O controller, and then the CPU, in this case, goes off to do something else. It starts executing other processes and so on. And once the device is finished, the I/O controller raises an interrupt, and then the device can, the OS can go look at the results of the request. Okay? And the last type of device driver that we talked about was DMA based, direct memory access based. And the reason you need this is if you want to transfer large amounts of data to the I/O device or from the I/O device, doing this one byte at a time is very wasteful and very time consuming. That's the standard way to interact with the device is do one byte or one word at a time. You read or write one word at a time. So the better way to do this for devices that need higher throughput is to put the data in a buffer, okay? And then tell the device controller saying, take the data from the buffer and write it up. Or you allocate a buffer and tell the controller saying, go read this chunk of data and put it in the buffer. Okay? So now the CPU doesn't have to issue request one byte at a time. The I/O controller can then go and perform the I/O in whatever granularity it needs to, and then the data is directly put in the buffer without any involvement of the CPU. Okay? The CPU is just given a command and said, go and do I/O on this chunk of data, okay, reading or writing. And then once the entire DMA operation is finished, you raise an interrupt, and then you have the COS can then go and look at the results of that. Okay, so these are three techniques we looked at last time. That's just a quick recap. And then towards the end, we talked about caching and buffering as a way to bridge the gap between a fast CPU and a slow device. Okay, so you can use the buffer to store frequently accessed pieces of data, so that when a request comes in, you first look at the cache in the buffer and see the data is already there, then you don't even need to perform that. Much faster if you have a cache. Okay. You also can use it to mask the difference between the size of I/O the application is requesting and the size of I/O the device may support. So in case of disk, you have to do I/O in granularity of sectors, but applications can perform I/O on file in any granularity. You can read or write 1 byte at a time. So what the device would have to do is read an entire sector, and from that sector pick the desired byte or few bytes that were requested by the application and hand it over. So the buffer is trying to bridge this gap as well. And I was describing what happens when you write to a cache, and we talked about the write through policy and the write back policy. Write through policy says whenever you make a write, it hits the cache and then you immediately send it to the device, so that there are no unwritten pages in the cache. So even if your power goes out and memory contents are lost because the buffer is stored in memory, okay, so if the power goes out, all of that data is gone. So if the power goes out, there is no unwritten data in the write through policy. In a write back policy, you're trading performance for reliability. So you write data to a memory buffer, and then you, in the background, asynchronously write it out. Okay, so in this case, applications don't have to wait for the I/O to finish. They can write to the cache, which is fast because it's writing to memory, and then have the OS flush that data off to a device. Okay. So typical operating systems made a design decision to go with write back policies because of performance reasons. Okay, but occasionally when you have power outages, your I/O may not have unwritten data may not have propagated to the device. That can cause problems. So that's where we left it last time. There's one more slide here which just says this is what's going to happen when you have a read request to an I/O device. So the user requests a read from a device. This could be a disk or any other device. Let's say then the first thing the OS has to do when it receives the request is this data that is requested already in my buffer cache. Okay? If it's in the buffer cache, that's called a cache hit. You are done. You just take the data from the cache and give it to the application that requested. Okay? And if you don't have a cache hit, a cache miss, then you are actually going to perform the requested I/O. So in this case, the OS is going to tell the device driver saying, you're doing a read, so you have to basically perform input. And let's say you're trying to read a larger chunk of data, so you use a DMA-based method to do the read. So this is a DMA-based device driver. So you will tell the DMA controller, so you go perform this read. Here is a memory buffer where you need to write the data that's being read. Okay, then the DMA controller is actually going to go off and read the data and put it in the buffer. Once this is done, you raise an interrupt, and then the OS will suspend execution of the process that was running on the CPU, will context switch into the kernel, will basically go back into the device driver, which will service the interrupt. Okay, and that basically is going to take the memory buffer that the DMA controller wrote to, and then hand it to the application. Okay, and then the process can resume execution. So this is basically a set of steps that you will have to perform, which involve the OS application and the device driver in the OS. Okay, just to give you a feel for how typical I/O operations are carried out in the kernel. Okay, so any questions on this before we switch gears and move on to the next topic? Okay, that's all we have. It's a short discussion on I/O. We just had about a lecture's worth of material. Okay, so the high level thing to keep in mind is there are different ways to write device drivers, and most of those have to deal with how the device talks to the device driver talks to the I/O device, which is typically slow. Okay, so you can use polling-based, interrupt-based, or DMA-based. These are 3 ways to write any device driver that you see in a kernel. Okay, so I will switch gears and we will move on to the next topic. So at this point, we have basically covered the 3 core components of an operating system kernel, all the aspects of the kernel that deal with the CPU, all the aspects of the kernel that deal with memory, and everything that has to deal with I/O devices, disks, and other kinds of I/O devices. So those are the core topics that we had set out to cover. We are done. Okay, done with those topics, not done with the course. So the last component is on distributed systems and networking. Okay? So this is the part of the OS that deals with your network card, whether it's an Ethernet card, as a Wi-Fi card, maybe on a phone, it has a cellular card. All of those require you to do network I/O. You're reading and writing data over a network. And so what does the OS do to enable that functionality. That's basically what is coming up in the next 2 or 3 classes. Okay, so that's basically this topic of distributed systems. I'm going to start with some networking basics. Okay, maybe some of you have taken 453, you know what a protocol stack is, but there may be some of you who don't know all of that. Okay, so I'm going to start with some very basic material on networking, what's a packet, what's a protocol stack, and so on. If you know all that material, bear with me, we'll be done with that very short order, and then we are going to actually talk about operating system aspects of distributed systems. So we'll talk a little bit about why it's beneficial to have a distributed system, what does it give us, and so on. And what you need to realize is most applications that you interact today are distributed in some shape or form. Whether it's your mail system, whether it's your network browser, whether it's some other application that involves talking to some other component. These are all examples of a distributed system. So it's instructive to understand what it is and what we need to do from an OS perspective. Yeah. The guest lecture is already done, so that's something that we are not going to actually do. Usually it comes up at the end of the course, but this time I had to put it up front, so that is all done. Okay, so only thing we are going to do in the rest of the course is distributed system topics. Okay, we'll talk about distributed systems, distributed file systems, excuse me, as well. Okay. So what we will do is we will start with a definition and some examples, then we'll look at some networking concepts, then we'll come back to distributed systems. Okay. So what is a distributed system? So here's a definition and there's a picture there. So it is a set of processors that basically can communicate with one another over a set of communication links. Okay? So think of a distributed system as a set of machines that work together over a network. Okay? To achieve some task. The task is the application that is actually running on this machine. So at its very core, a distributed system is simply a set of, I just said processors there, I could just say machines, but we'll see why you have to say processors as well. Okay, so because you may have more processors than machines on them. But, so here's a picture, it shows there are 5 machines, P1 through P5, which are 5 processors, one processor each, they talk to one another over a network. The network could be any kind of network. It could be a local area network, it could be the internet, it could be a wireless network. What the network is not important here. Okay, so any kind of network that enables communication will work with this definition. Now, as I already said, most applications that you use on a day-to-day basis actually are distributed. Okay, so think of email as your example application. Okay, so email systems are distributed. There's a mail server, okay, that runs on some machine, okay, and there's your mail client, which could be a browser if you're using webmail. It could be a mail client like Thunderbird or Outlook or Mac, so mail client, whatever the client is. That's another part of the application that runs on a separate machine. And these two components communicate with one another over a network. Okay? So that basically complies with that definition. Okay, so that's mail. So if you look at the web, that's an example of a very large distributed system. Okay, so what are the components you see in the web? Okay, there are web servers. What else? What did you say? DNSs. Okay, DNS. What's the client? Somebody said something earlier. Oh, you said. What did you say? Oh, you said. Website. Okay. I meant client to access the website. It's a browser. Right? So the web consists of servers, which are HTTP servers and some other components that will sit behind the server, and web browsers. Yes, that's an example of a distributed system because the browser runs on a machine, it connects to a server that runs on a different machine, 2 machines communicating over a network. Okay? And you can take any other application that you think of. You have file servers that work this way. If you go to the EdLab setup, you will see that you have home directories and course directories that sit on a file server. Okay, that's where all the data resides. And then there are clients, which could be workstations or there could be a laptop that you're used to remote login that are actually accessing that data. Okay? That's another example of a distributed system. And you can keep looking at many other applications. There are network printers and databases and so on. But you get the basic idea. You have an application or component of the application that run on different machines and communicate, okay, to achieve a certain task. So it is instructive then to understand what allows you to do all of this, at least from an OS standpoint. Okay? A lot of the more advanced material for this is part of a graduate level course, so we are not going to look at those details here, but you'll get a basic idea of networking concepts and how that is used to implement a distributed system. Okay, so before we go on, I want to take that definition I put on the previous slide and try to peel it apart a little bit, okay, so you get an understanding of what distributed systems are. Okay, so at some level, there are two types of systems where you have multiple processors that communicate with one another to achieve some task. And you can actually loosely define them as a parallel system and a distributed system. Okay, so, and also a tightly coupled system or loosely coupled system. So in a tightly coupled system, which is a parallel system, you have multiple processors, but they are all processors inside a machine. Okay? The communication medium is some sort of an interconnect, like a system bus. Okay, so you can get very high-end multiprocessors that may have 128 processors, 256 processors, and so on. And then you have interconnects that are sophisticated forms of system buses. But all of those processors are inside a box. Okay, that box is the machine. Okay, so that is what we are going to call a parallel system. Okay? Now, if you have processors that are independent machines that then talk to one another over a real network, that is a loosely coupled system. It's called a distributed system. So I want to distinguish between a parallel system, which also has multiple processors and an interconnect, from a distributed system where the processors are independent machines. Okay? In some cases, the distinction is somewhat blurred. People use some form of parallel systems and call it a distributed system, but we are going to distinguish between the two. Okay, so in a loosely coupled system, each processor has its own memory, each processor runs an independent OS, and communication is actually taking place over a network. In a parallel system there are independent processors, but they may share memory. Often they do share memory. Okay? They may have a common clock, and frequently they run the same OS. They don't have to. You can actually run multiple instances of kernels on different processors, and that's still a parallel system. But typically they would run one OS. Okay? Need not be. But what is true is that they will actually share memory, and they're all inside a box, and there's an interconnect that sits inside. Okay? So we'll distinguish between the two, but so you should know what is a parallel system and how it is different from a distributed system. So any questions on this? Yes?
So is a parallel system just like any computer with more than one processor?
So you can basically think the simplest form of a parallel system is any computer with multiple cores. Your phone could be a parallel system with dual core, for example. But really that definition is meant for much larger systems that are, the definition applies even to any multi-core system. There are real servers that are 128, 256 processors, high-end interconnect that really look like a network, but they're all inside a box. So we're going to call it something that's not quite a distributed system. Yes. Any other questions here? Okay. All right. So now we should, before we go into all the networking stuff, we should say, why did we want to build applications that run on a distributed system? What does it give us? Okay, so we'll look at two benefits. Okay, there are some more, but on this slide we have two benefits, which are resource sharing and computational speed up. I'm going to start with the second one first, just to give you an idea. Okay, so what does computational speed up? So in a distributed system, your application is split into smaller components that run on multiple processors. And so if your application runs on n processor, it follows that it can harness the CPU cycles of n processors. So if you actually build your application well, typically you should get n times the throughput or n times the performance or n times the speed up of the same application if it was implemented on a single processor. So you are basically spreading your application or distributing, technically distributing your application over multiple processors, and hence you are able to get the take benefit of the presence of these processors and the cycles of these processors. So you are going to essentially get speed up. So n processors potentially give you n times the computational power. Okay? But to take advantage of that, you need to take your application and split it into pieces such that each piece runs on a separate processor. Okay? So you need to be able to write your application. For many client-server applications, this is natural. Okay? Web browser runs on one processor or one machine rather, and the server runs on a different machine. So that's a natural way to decompose your application. But you know, other applications that need some more careful thinking into how to do the decomposition. Okay? And there's frequently coordination and communication between these processes that run on this processor. So your application components are talking to one another. The browser sends requests to the server sends replies back, and so on. Okay, and they may actually have more sophisticated forms of message exchanges as well, not just a request-response type message exchange. Yes?
Wouldn't it be like extremely slow to be sending information over the network?
Okay, so that's a good point. The point is, wouldn't it be extremely slow to send information over a network? Indeed, that is a problem. If your application requires frequent exchange of data or messages, and you're doing this over a network, it is going to slow down your application. Okay? This is why I said if you actually have a parallel system where all the processors are inside a box, you have a very fast interconnect, you can actually run applications that are very frequent communication, and that is the preferred kind of hardware to run those kinds of applications. Once you become really distributed, you have a slow network. Your network is relatively slow when you compare it to the speed of the processor because it's a communication medium. So the moment you start sending messages, you're going to be blocked waiting for replies. You cannot make progress. Okay? So that is an issue you have to deal with. Okay? That depends on how you write the application. Okay? So, but nevertheless, if you do this well, you will get the benefit of computational speed, okay, which you wouldn't have if you had a unique processor system that was running all components of your application. Okay, the second thing which is also very important is the ability to share resources remotely. Okay? The simplest way to think about it is you store data on a machine. Okay? You access the data from a different machine. Okay? So that allows you remote access. So you're able to share the disk of the first machine on the second machine. You do this by creating a network drive. You can mount the file system, or you can create network volumes. Okay, if you've done any of this, you know how to access data that's stored on a server, okay, on a file server in this case. That's an example of resource sharing. You are able to use resources on other machines. In this case, you can store data on a different machine. Okay? Maybe your machine doesn't have enough disk. You can put the larger files on a server. Okay? You can also put it on a cloud. That's an example of a distributed system, okay, where the storage is on a cloud. Okay? So you are able to access resources remotely, and you are able to share these resources remotely. The same is true of a network printer. Okay, if you have a printer that's network, you can print to it from anywhere. You don't actually need it to be plugged into your machine in order to print. So this gives you the benefit of accessing or having print services over a network, even though the resource is not local. So resource sharing is an important benefit, and it's an especially important benefit if the resources being shared are scarce. Okay, you don't have a printer for every device you own. Okay, you don't have a printer for your phone and a printer for your laptop. You have one printer that is network, and then all of these devices can print. Okay, so that's an example of sharing expensive resources so that you don't need to have one for each machine, okay, or each device on your network. Okay, the last benefit there, communication I already talked about. The last benefit is reliability. Okay? So in a distributed system, since you have n machines, if one or more machines fail, okay, the application as a whole, if it is written well, can continue to function. Okay? In a centralized system where there's only one machine, if that machine goes down, whatever application was running on that machine stops. So distributed system can give you better reliability than centralized system. That's a simple observation that you can make. Okay? Now that's not always the case. Okay, you want to write your application. Just because I said you have n machines, sure, if one machine goes down, the other machines are up. But if that machine was running a critical component that you have not replicated on some other machine, if that machine fails, your application may not function. It may say, I need to access a database, the database has gone down, so nothing can be done. Okay, if you don't really write a distributed system such that the database can actually be restarted or is already replicated on some other machine, that benefit goes away. But if you write your application well, then you will get the benefit of reliability. It says if some machines fail, the others can take over the work that was being done by those machines, and hence application can continue as if nothing has happened. Maybe it has less resources, but that's all that you actually have to deal with. Okay? It's a very important benefit. Okay? Most distributed applications actually rely on this fact, especially any application that you use on a day-to-day basis. Let's say it's a Google search engine, or it's Facebook, or whatever other application that you think about that you are used to. Okay, so you have to realize that those applications are distributed on lots and lots of machines, and they are written in a way that even if some of those machines fail, the application continues to function because other machines take over the work that was being done by the failed machines. Okay, so this way users are not inconvenienced. You don't see a scenario where, okay, the search engine is gone down, so I can't do Google search anymore or anything like that. So that's the important benefit of distributed system. Of course, distributed system enable communication, so real users can send messages and all of that. So that's what the last point says. Okay. So with that in mind, now let's come back to our goal of looking at operating systems and looking at what are the basic functions you need inside an OS to implement all of these good things that we talked about in distributed application. So the first thing is your operating system needs to implement functionality to allow you to write applications, okay, that will be distributed. And we'll look at one such function, which is remote procedure calls today, once you have done a little bit of networking. Okay. But there are lots of other things that you have to deal with, and we are not going to go into all of these things in this class, but all of the benefits that I talked about, okay, reliability, the ability to do resource sharing, it all needs some OS level support. Right? So for instance, how is the OS going to allow you to access data that was stored on one machine from a different machine? Okay? That's an OS function. What that actually requires you to do is take your file system on your machine and somehow allow access to that file system from a remote machine. That makes it a network file system. Okay? So the OS has to make your local file system networked in something. Okay? That requires additional functions in your file system that can now accept requests not from local application but requests from remote machines that are being sent to this file system so that you can retrieve that file and send it over. Okay. So you have to basically implement additional functions. The same is true of reliability, security. We have really not touched upon in this class, but it's an important aspect of distributed system because you can now access resources over a network. Okay. It's not just legitimate users who can access it, so can malicious users. So how do you protect your distributed application from unauthorized access? From people who are trying to now hack into the machine because you can access the resource and so can someone else. You don't want to make your files accessible to anyone in the world who just chooses to send a request to your file server. Okay, that's not going to work. Okay, and same is true of any other type of data or resource that you have distributed. Okay. So that's a function that you will implement inside the operating system, which we are not going to look at in this class at all, okay, but that's an important aspect. The reliability is another important aspect. Okay, one machine goes down, how is another machine taking over its work? Okay. The OS has to implement functions that realizes that some machine went down and now requests that are coming in are somehow being sent to the previous machine or the machine that's still up and it takes over the work and so on and so forth. Some of this needs OS level function. Some of it is done in the application. So these are all things to keep in mind as to the operating system functionality becomes more complicated because you have to implement all of these features or some aspect of these features inside the application. Okay, the programming model is also important, which says how do you basically write programs or applications that can communicate with other applications. So we are going to look at that aspect. Okay, that's remote procedure calls or remote method invocation. Okay, it requires some OS level support, and then it requires language level or compiler level support. Okay, and so those are all things that you have to deal with when you write distributed systems. Okay, and before we talk about networking, I'm going to say a little bit about what things get harder from an operating system standpoint. Okay, so all of the synchronization stuff that we talked about becomes a lot more complicated. Okay, so you still need locks, you still need to detect deadlocks, you still need to do synchronization, but now this is not across processes or threads on the same machine. These are processes that reside on different machines. Okay? So how do you write a lock for 2 processes or n processes that run on 10 machines? Because they are trying to coordinate some tasks, so they need to ensure that some mutually exclusive access to, let's say, a resource. Okay? So now you need to create a distributed version of a lock. How do you detect deadlocks? Okay, when you have locks that are distributed, you may have a deadlock. How do you detect deadlock over a network? It's a very complicated issue. Okay? How do you detect failures? I mentioned some of this already. Resource sharing as well. Okay, so all of these things make the OS much more complicated. Okay, so what we have really looked at in this course so far is a centralized operating system that is servicing processes that run locally. Okay. But OSs also service requests from processes that run on other machines that might be doing all of those things. Okay, so that's basically where you get into designing distributed operating systems, not just centralized operating systems. Okay, so with that in mind, I'm going to basically spend some time doing a quick overview of networking, and then we'll come back to distributed systems and start today with the programming model. And then next time we're going to look at distributed file system. We'll look at the file system concepts we studied the past few classes, and then say how do you make that a distributed file system. Okay, so those are 2 components that will give you some flavor of designing distributed systems. Okay, but we'll start with some networking background. Okay, this is all stuff that is typically covered in a networking class like 453, but since you will not have taken it, this is just the basic things you need to do. Okay? So, what is a network? It basically is a communication medium that allows applications, processes to send messages between one another, communicate with one another. Okay? There are 2 kinds of networks that you should at least know about: a local area network and a wide area network. Okay, local area network is a network that connects machines, let's say within a building or within a campus. Okay, the geographic distance between machines is small. Okay, there could be just a set of machines inside a room, for example, a set of machines inside a campus. So examples of a local area network, Ethernet is a good example. Wi-Fi networks are examples of local area networks. Okay? And typically when you have local area networks, you get higher communication speeds or bandwidth. Okay? You may have 100 megabit Ethernet, you may have gigabit Ethernet that allow you to send 100 megabits of data, up to 100 megabits of data every second, or gigabit data. Okay, the same is true of Wi-Fi networks. You can have 802.11, A, B, C, N. Each of these numbers depict a certain type of a Wi-Fi network, and each new technology allows you to communicate at higher and higher speed. So you can do 54 megabits per second or 100 megabits per second communication over the wireless. Okay. So local area networks typically are designed to communicate, to allow machines to communicate over short distances at higher speeds. Okay. Wide area networks, on the other hand, also called WAN, are networks that connect machines over much larger distances. They could be across a state, across a country, and across continents. Okay? The most prevalent example of a wide area network is the internet. Actually, the internet is not itself a wide area network, but it's a collection of wide area networks that are themselves interconnected. Okay? So it's a network of networks, but you can think of it loosely as a wide area network that spans the entire globe. Yes, but you can also have other forms of wide area networks as well that are embedded in the internet. So the thing to keep in mind is because the distances are larger, the speeds are slower. Okay, you are not going to be able to send gigabit. So you may have 1 megabit. So when you actually construct a wide area network, you have to lease cables that are actually laid from one region to another, and then basically get a certain type of network. So if you get what's called a T1 line or a T1 network, you may get 1 megabit per second. Okay? If you go T3, you'll get 45 megabits per second, and so on. Okay? If you have a cable company that gives you broadband access, that's an example of a network that connects you to the internet. Okay? So you may get 10 megabits per second connectivity from your provider. If you have a cellular phone, you will get a certain speed. Okay? That depends on what kind of technology you are on. But they are all much less than, let's say, a LAN which may give you gigabit speed or 10 gigabit speed or 100 gigabit speed as new LAN technologies come. So WANs connect you over longer distances, okay, but they are slower in speed. So those are the two types of networks you should know about. Okay. So now let's talk with that in mind. Let's talk a little bit about how communication actually occurs over a network. So the way this works is you want to send, so if two applications or processes want to communicate, they are going to send messages back and forth. Okay? Messages in place of data that they're sending back and forth. And what happens at the network level is that the data is chopped into packets. Okay? There are smaller chunks called packets, and packets are the basic transmission unit for a network. So then the packet is actually sent over the medium, it traverses the medium, it arrives at the other machine, and then it's handed to the application that it's supposed to be sent to. Okay. So, and then there are, between the two machines, there are other intermediate machines which are called routers or switching units that are going to basically ensure that the data makes its way from the source machine to the destination machine. Okay. So the way the analogy here is really, you can think of it as how cars traverse over a road. In this case, the road is basically the medium that allows the transportation, and the cars are entities that traverse through this medium. So in the networking world, the data packets are essentially analogous to cars, and the roads are the medium that enable communication is analogous to the network. So and then, as you can imagine, each car traverses from a source to a destination and takes a different path depending on where it needs to go to. In the same way, each network packet may take a different path through the network, traverse a separate set of wires or links, depending on what's the source machine that sent the packet, and what's the destination machine that needs to receive the packet. Okay, so that's sort of the way to think about this. Okay, and just as in your transportation example, you can have traffic congestion or traffic jams. You can have the same kinds of problems in a network. Networks can get congested if there's a lot of data that's trying to flow through a link. The link may get overloaded, it's called congested, and that may slow down your network. So same kinds of ideas apply even to networks. Okay, so I'm going to show you this slide which depicts what is called a protocol stack. Okay, so you probably have all at least heard of TCP/IP or even know what it is. TCP/IP is an example of a protocol stack. And here's some more formal definition. Okay, so what's a protocol? A protocol is a set of rules for communication. Okay. When two processes want to communicate over a network, they need to agree on some rules. Okay, which says this is what each packet will mean, and this is how you understand what I'm saying in you, and so on. Okay, just as when you actually talk to someone, the rule that you agree upon is what language you're speaking. If the other person doesn't know English, then you may try to communicate, but he or she won't understand what you're saying. So you need to at least agree on what language you are going to each speak and understand. Okay? The same is true in the network. The protocol is like a language, it's a set of rules. If the other machine doesn't understand your protocol, then you can send it data, but it won't be able to decipher it. It won't understand what's in that data. So two machines that try to communicate need to speak the same language, which means they need to use the same protocols to communicate. So that's a fundamental assumption that we make. Okay? Now that in these days the language that most machines speak is TCP/IP. Okay? Those are the rules that machines communicate with. But that's not the only protocol stack that is available. There are many others, but TCP/IP is the most common and the most prevalent one. Okay? So what is shown here is the set a typical protocol stack on a machine. Okay? And here we are actually showing, this figure is showing 3 machines, A, B, and C. Okay? You can think of A as the sending machine, C as the receiving machine, and B is an intermediary. Okay? Typically it's called a router. Okay? So that's the one that is going to sit between A and C. Okay? And you will see that there are layers or boxes here. These are different components of your protocol stack. Okay? So you have the physical layer, the data link layer, network layer, transport session, presentation, and the application layer. So applications actually sit at the top, highest layer of the protocol stack. So here is your client, say this is a web browser application here. This could be a server, and then the server would actually be part of that layer on the other end. Okay, so those are the applications that talk to one another. Even applications have to agree on a protocol. In the web, the protocol that they speak is HTTP. So that's the application level protocol that's used in the web. You use mail, you use SMTP, simple mail transfer protocol. So there's a protocol that the applications speak, and then each layer has its own protocol. Okay, when you say TCP/IP, the TCP part is a transport level protocol. Okay, so both of these layers have to talk TCP for the communication to take place. Okay, the IP part of TCP/IP, which stands for Internet Protocol, is a network layer protocol. And I'll talk about what this means in just a moment. But so both ends have to speak IP, and then at the transport layer, both ends have to speak TCP. So this is a web application. Both application layers have to speak HTTP. Okay, and if they all do that, then the two entities can communicate with one another. So essentially, at each layer, you have to use the same protocol, speak the same language. Now let's talk a little bit about what these layers mean. Okay? So if you remember when I was talking about the layered approach to OS design, okay, so I said the only place where it's actually useful is the networking component of the operating system. And the reason that is the case is the network protocol stack is designed as a set of layers, where each layer only talks to the layer above it and the layer below it. Okay? And the way communication takes place is, let's say your sending application wants to send a message to the receiving application. Let's say the browser wants to make an HTTP request, okay, request a web page to the server. It's going to construct a message saying send me index.html or whatever web page you want. Okay, and it's going to construct a message and hand it to the layer below it, saying send this message off to the server. The layer below it is going to do some processing, okay, to that message and send it to the next layer below it, and so on. Okay, so your network packet is going to traverse down the protocol stack. Okay, this is still the machine and the OS on the machine, and then eventually it's going to be sent over the actual network. Okay, that's the communication medium. It's going to traverse the network. Okay. It may actually traverse a number of intermediary machines, each of whom send it to the next machine on the path from the source to the destination. Okay, this is the path your packet is going to take. It's going to go from A to B and B to C. Okay. So each router is going to then send it to the next one. Here it shows only one router that sits between the sender and the receiver. So your packet is going to go here. From here it's going to reach the server machine, which is C, and then it is going to make its way up the protocol stack. So this network packet is going to be processed by each of the layer, and it's going to be handed to the layer above it, and then it's going to reach the application. Okay, now that's the web server. It receives at this point an HTTP request from some browser on some other machine. Okay. So it's going to process this request. Okay, the request is to fetch a page, index.html will say. So it's going to fetch the page, construct another message, and here is my reply. Okay. And then the whole procedure is going to take place in reverse. That request packet is going to traverse down the protocol stack, go over the network, appear at the receiver, and then traverse up the stack, and then the browser will finally get its page. Okay. So that's basically how communication takes place. Okay. And all of these components are inside the OS kernel, except for the application, which is obviously the application process itself. But everything else is inside the kernel. Okay, so you just hand it a packet, and it's going to process it and eventually send it over your Ethernet card or your Wi-Fi card or your cellular card if this is a phone. Okay? So any questions on this? Okay, so let me say a few words about what these layers themselves mean. Okay, so physical layer essentially is a physical medium itself. What is the medium used for communication? You have Ethernet, this is going to be the wire that you basically connect to your machine. If this is Wi-Fi, that's the channel that you send your packets on. If that medium is cellular, then that's your cellular medium or whatever medium you are using to communicate with your cell phone tower. Okay, so the physical layer is the lowest layer of the protocol stack, and that's the actual communication medium. Okay. Now the data link layer is basically a layer that is going to allow you to construct a packet that you can send over the physical medium. Okay, so if you are actually sending it over the air, you have to basically use some form of wireless transmission. You're sending, and then you use a data link layer that's going to do that. If you're going to send it over a network, you're going to basically use a data link layer that's designed to work over wires and so on. Okay? So Ethernet is an example of a data link layer protocol, also called a MAC layer protocol. Okay, so you must have heard of this MAC ID and so on. And that all of that is basically, that's called access control. So that's the layer that sits right above the medium. Okay, so Ethernet is an example of a data link layer. Okay. Now what sits above Ethernet is what's called the network layer. The network layer is responsible for what is called hop by hop communication. It sends a packet one step at a time to the next machine. That is all it does. It figures out when a packet needs to be sent, what is the next machine to send it to. Okay, as I mentioned, a packet can traverse multiple hops or multiple machines before it gets to the destination. Okay? It's the same as you send a package through the US Postal Service. It may traverse multiple intermediary points before, or multiple post offices before it gets to the destination. The network protocol is simply going to decide what is the next machine to send it to. So the network protocol here is saying what's the next machine, and saying let's send it to C. So you just send that packet. And when it arrives at C's network layer is going to say where should I send it next. And in this case it will say B's network layer is going to say where should I send it next. The answer is C, so it gets to C. But you may traverse any number of hops. Okay? And the network layer decides how to do it. So the context of TCP/IP, the network layer is IP. Okay? It does what is called routing, which is basically the decision making of how to send it one hop at a time. Yes, question.
How does a network decide which node to send it?
Okay, that's a good question. Question is, how does the network layer decide how to actually decide which node to send it to? Okay, so this technique is called routing. Okay, and the way things work is every packet, I didn't say what a packet contains, but typically a packet contains the sending address and the receiving address. Just when you send a piece of mail, you say what's the destination address, you write the address and then you write sender's name. Okay, so the same is true of a network packet. You will have a receiving address. Typically that's an IP address of the receiving machine, so you don't need to worry about that. So you are basically going to send the destination address. Okay, so the packet needs to get to some destination. So then basically each network layer is going to say it needs to get to this machine. What is the path that it should take to get there? And what is the next machine in the path? So you're basically going to say, so think about this, you want to travel from, let's say, here to California. You're taking a long road trip. Okay. So you need to first chart out the route. Okay. And then at each point, let's say you go from here to Philadelphia. And you say, if now I've arrived at Philadelphia, I need to get to California, what's the next place I need to go to? So you're going to make a route. It says, this is the path I'm going to traverse. Okay, the same is true of a network packet. You're going to basically have a path from the source to the destination, and each node will look at the destination and says, I need to make progress. I need to get closer and closer to the destination. So what is the next machine I can send this to so that it is actually one step closer to getting. Okay, that process is called routing. You're going to use the destination address to decide what is the next node to send it to. Okay, so again, all of that is typically something you'll learn in a lot more detail in a networking class. But the thing to keep in mind is network layer does routing. It decides hop by hop communication, which keeps sending the packet to the next node and so on. So you need to know where it needs to go to, otherwise you cannot figure out what's the next node in the path. Okay. Next layer up is the transport layer. The transport layer is responsible for what is called end-to-end communication. Okay. The network layer does one step at a time, hop by hop. So it says A to B, B to C, and so on. The transport layer is actually end-to-end. Okay, it does things like if I send a packet, okay, and it gets corrupted on its way. Okay, arrives at the other end, but it's corrupted in some shape or form. It's the job of the transport layer to make sure that a new copy of the packet is sent so that you actually get the packet that was sent, originally meant to be sent. Okay? So it basically sits at the two ends, at the sender and the receiver, examines the packets, makes sure no packets get lost, make sure they arrive in the same order, do all of these things. It also decides what speed to send the packets at, because if you send it too fast, you may actually have problems in the network. You send it too slow, your users will say the network is really slow. So you have to find the right speed to, otherwise one rate to send out packets and so on. Okay. So in the context of TCP/IP, TCP actually does this for you. Okay, so it's going to do end-to-end communication, it will do error recovery, it will do retransmissions, it will do rate control. All of these things are actually done at the transport layer. Okay, yes? End-to-end is the sender and the receiver. You'll see that there's no transport layer on any intermediate nodes because they don't actually need to do anything. You're only looking at the sender side and the receiver side, and those two protocols talk to one another saying, did you receive, every time you receive a packet, you send an acknowledgement saying, I received packet 10, I received packet 11. And then the sender can say, looks like you did not receive 10 because you're telling you received 9 and 11. I didn't get an ad for 10, so you'll retransmit them. So you can do these kinds of things. Okay. Now there are these two other layers. One is called a session layer and a presentation layer. The session layer, typically in a TCP/IP world, the session layer and the presentation layer are actually handled by the application itself. But there are some protocol stacks where those layers exist. So you can think of a session layer as doing things like SSL. It encrypts your traffic because you don't want the packet to be sent unencrypted. And others can actually look at the content of the packet and figure out there's a password in there and so on. So any data that's sent by the application, you can send it to a session layer, the session layer can encrypt it, and then at the other end, the session layer will decrypt it. And so then what comes to the application is exactly what was sent, but everything in between is automatically being encrypted. So if you use things like SSL in web, so the session layer is actually going to do the encryption. And the presentation layer can do things like formatting of the packet so you can actually figure out what it is. But typically, as I said, this is done within the application itself when you construct the packet, but you can have special layers in the protocol stack that do that. In TCP/IP, you don't have a presentation layer either. Okay? So that's a very quick recap of what is a packet and what's a protocol stack. So I'm going to see if there are any questions here before we move on to some other concepts. People clear on at least some basics of a protocol stack? Okay, so this is just a definition of whatever I said, so I'm not going to repeat this. Okay. And here is an example of how that picture maps onto TCP/IP. As I said, your layer 1 is, in this case, showing the Ethernet, which is 802.3. Okay, if you have Wi-Fi, that is going to be 802.9. These numbers just tell you what is the protocol. Is it a wired, wireless protocol, and so on. And you see what sits above there is the network layer, which says IP. And what sits above the network layer is the transport layer, TCP. TCP has a sort of sister protocol called UDP, which is sometimes used, but very often it is not used unless you need a special scenario. And then everything else sits above that. So you see things like HTTP, FTP, SMTP. These are all protocols used by whether you have mail application, web application, file transfer application. So those are all application level protocols, and then there's a user itself on an application that actually uses those protocols that sits on top. So this is just showing you what I just said, but in a pictorial form. How network, data link layer, the network layer, transport layer, and the application layer map to what you actually see today in terms of using TCP/IP based applications. Okay, so the only last point I want to say is I mentioned that UDP is another transport layer protocol, stands for User Datagram Protocol. It's a much simpler form of a transport protocol that provides no reliability. Okay, TCP is a reliable protocol, which means if a packet is sent, the sender will keep resending it until it's actually received at the other end. Okay, so if packet gets lost in the network, gets corrupted in the network, you keep resending it and it's received successfully. Okay? So the application doesn't have to worry about what happened in the network and created some problem for my messages. You can TCP will deal with it for you. Okay, UDP is a simpler protocol that does not provide any reliability. It doesn't retranslate packet. A much simpler protocol. It is typically used in LAN environments where the network is reliable, generally speaking. So you don't really need to have additional overhead of tracking which packets were sent and or got corrupted and so on. So in environments where the network is very reliable, you can get away by using UDP. When you send packets over a network, it's always better to use TCP because the internet, anything can happen. Routers can discard your packets can get corrupted and so on. But if you're on a LAN setting, your home network or some such thing, you may have reliability that you can actually run UDP-based application. Many gaming applications actually use UDP because it's faster, because of its lower volt. So if you're a gamer, you may actually have games that actually use UDP. Yes, for sure.
Like video and audio streaming, is that also UDP?
So I was going to say something about video and audio. So when you have audio and video streaming, the original protocols actually used UDP because it was faster. And in some cases, when you're actually receiving a video stream or a network, getting a late packet is as good as not getting the packet at all. Because let's say you're watching a movie, okay? You're missing a certain image in that movie. Okay? Now you're continuing to play. So if you already played beyond that point, getting that this packet late doesn't do you any good. You're not going to rewind and say, I missed that, I'm going to start from there. You've already gone past it. And so early video protocols actually just use UDP that if some packets get lost, that's fine. You'll see a glitch and you'll basically continue from that point on. Some audio will have a gap and then you'll just continue. And then you'll just see bad quality for a little while and it will recover. Okay? Now having said that, today video and audio actually run over HTTP, okay, which is the web, and HTTP itself uses TCP. So it's no longer the case that audio video streaming are not using any reliable protocols. They do, because most of what you see, Netflix, YouTube, Hulu, all of those actually run over HTTP and they're just using TCP underneath. Okay, so TCP has become the default even for audio and video streaming. Yeah, so with that, there's one more thing here. So here's a picture of what a packet looks like. So I just sent a packet without actually showing anything. Here is an example packet. So this is a chunk of data. Okay? And what is in the middle here is the actual data that the application is sent. Okay? So when the packet is being processed by the protocol stack, each layer of the protocol stack adds some extra information. It sort of appends the information to the packet. This appended information is called a header. Okay, so you will see the header contains many different things. Okay, so this is the IP header. This is the header that an IP part of TCP/IP will add. So you'll see that the header has something called a destination address, has something called a source address. It may also have a port which says HTTP runs on port 80. It will say this packet needs to go to port 80 and so on. So the source and destination address is typically your IP address. Okay, 128 or 119, whatever that number is, that's the number that you actually have in the address. So this is what routers are going to use for routing. So the packet needs to get to a machine with that address. What do I do? Where do I send it next so it gets there eventually? So that's an example of headers that are added to the packet. Each layer is going to add its own header. Okay, that's an IP header. And then there will be a TCP header. There's going to be an HTTP header. When the Ethernet frame is sent out, there's an Ethernet header and so on. So your packet will have a data and a set of headers. Each header is added by whatever layer process that packet. And then that is used by the other machine at the other end to do the final receipt processing. Okay? So that's what typically a packet would contain. So you have the data itself, which is called the payload. The payload just means that's the actual applications and data. And then there's all this extra information that are referred to as header information or metadata for the packet, which allows the protocol to figure out what to do with this data. Where does it need to go? Okay, so here are some example networks. Okay, this is basically what is called a network topology, just to give you some sense of how you can construct network. The simplest form of network is called a fully connected network. In a fully connected network, each node in your network has direct connectivity to every other node in the network. It's called a clique. If you've taken 311, you know what that means. So there's a direct one-step connection between all of the nodes in the network. So if you are a wired network, you literally have a wire going from every machine to every other machine. Okay? That's called a fully connected network. Okay, so this should tell you that, so typically if you have n nodes, then you have order n square links in this node, in this type of topology. Okay? So now most networks won't be fully connected in this form. You're not going to have a wire, literally one wire going from one machine to every other machine on your internet. That doesn't work on scale. So this is not necessarily a practical way to build a network, but that's the most basic way. It's called a fully connected. Okay, what you have typically are other forms of topology which are partially connected. In partially connected, you may have wires or connectivity between some subset of the nodes. Okay, typically, you may have, if you have Wi-Fi, you are connected to one or more access points. So that's your link. The access point itself may be connected to a router, and the router may be connected to a few other routers, and so on. So each machine is connected to one or more other machines in the network, but not every other machine in the network. So that's called partially connected topology. Most networks look this way. Now, this is clearly much more efficient to build because you don't need a link from every node to every other node, but it's more prone to failures. Because if some critical node goes down, your network is going to get partitioned. So for instance, if your home router goes down for your broadband connection, your home network gets isolated from the rest of the internet. So now you're disconnected. If you have multiple links, then you could have still sent your packets to some other paths. Because only one node has gone down, but there will be other links that are available to you. So in a fully connected network, there are more paths, and hence you have better chances of sort of not getting partitioned. The partially connected network, that's not the case. So you may have failures that can cause partitions of your network. Okay, now there are some structures you can impose on it. Okay, one structure is a tree-structured network where you have a hierarchy. Okay, so you have nodes that have parent nodes, and the parent nodes have other parent nodes, and so on. So the way the packet traverses is you basically keep going up the hierarchy until you have a common ancestor, and then you start descending down the hierarchy until you reach the sender or the receiver. Okay, so if the sender wants to send a packet to a receiver, the routing is going to say go up the hierarchy until you hit the first common ancestor, which is a common shared ancestor between the sender and the receiver, and then you come down the hierarchy. That's how packets are going to flow. Now, a common scenario where you use a tree-structured network is the internet is hierarchical. Okay, as you know, every machine will have a name associated with it. So you may have something like www.cs.umass.edu. That's a hierarchy. Okay, so it says this is the web server, the organization it belongs to is CS, that itself belongs to UMass, and the UMass is part of EDU, which is all machines that are all machines, all organizations that are educational. Okay. So the DNS is a hierarchical network. Okay. So DNS is the domain name system which assigns names to machines and IP addresses to machines. Okay. So that's a common example of a tree-structured topology that is actually used in the internet. Okay, you can have other topologies like a star topology. The star topology, there's one central node and all other nodes connect to that node. Okay, so if one node wants to send a packet to another node in the star topology, you send it to the central node just relays it to the receiver. Okay. Your Wi-Fi network is a good example of a star topology. Okay, your Wi-Fi router is the central node. All the devices that you're connected to your Wi-Fi router are all the nodes that are part of the star. So then if you want to have a laptop and let's say have some other machine and you want to talk to that other machine, your machine will send a packet to the router will send it back to the other machine. So that's an example, a common example of a star topology. So it is commonly used in local area networks or LAN environments. Okay, you can have a ring topology where your machines are arranged in form of a logical ring. Okay, so think of you have all the machines that you arrange them in a ring, and each node has two neighbors, a left neighbor and a right neighbor. So when you have a ring topology, you want machine I wants to send a packet to machine J. You can send it clockwise or anti-clockwise. It depends on whichever is closer. Okay, so you find the faster of the two, and then you basically keep sending it around the ring until it gets to the recipient. So routing is very straightforward. You already know what's the next step. If you got a packet from your left neighbor and it's not your packet, you simply send it to the right neighbor. And it keeps propagating until it hits the destination. So it's a very straightforward form of routing. Ring topologies were at one point very common local area network technologies. Okay? No more, because Ethernet took over. Okay? Back in the 80s and 90s, if you wanted to buy a PC, you had to specify which type of card, network card it came in. You could either get an Ethernet card or you could get what was called a token ring card. So your organization would have chosen one of these two technologies, and if you had chosen token ring, then it had connected all of its machines in a big ring. New machines come in, you have to insert it somewhere in there. And Ethernet is just connected to a switch. So it's a different technique. Okay. Now clearly Ethernet won, so you don't actually see token ring based networks anymore. But the one place where you still use it is if you have peer-to-peer networks or P2P networks. The ring topologies are used by these applications to construct logical rings and enable communication and so on. So there are some form of P2P or peer-to-peer applications that actually use ring topologies in a logical way. Okay? When you have two forms of ring, you can have a unidirectional ring where you want to pick a direction. All packets either go clockwise or all packets either traverse anti-clockwise when they are going over the network. And you can have bidirectional where you can pick which direction to use. So there are two forms of rings, and depending on which one you may have messages that need to go up to n-1 hops in the worst case for a message to go from the sender to the receiver. In a bidirectional ring, the worst case travel time is n over 2 hops. Okay? The worst case is I send a message that's to a node that's diametrically opposite to me, so it has to traverse half the ring to get there. Okay? So that's the number of hops, which is the number of steps you have to send the message for it to get where it needs to go to. Okay, so you can also have doubly linked ring, okay, because the problem in a ring topology is if some node goes down, your ring is no longer in existence. Yeah, I just switch off my machine and go off. Okay, so now then the ring is destroyed because each machine in the ring is actually sending packets to the next machine. So that switch off my PC, the whole network is gone. Okay, so to prevent problems like this, you can have a bidirectional or not bidirectional, but doubly connected ring or multiply connected ring, where you're not only connected to your next neighbor, you're also connected to your neighbor's neighbor. Okay, so you basically see that each node here, so this node is connected to two neighbors and it's also connected to the neighbor's neighbors. Okay, so if the neighbor goes down, you can actually hop over the neighbor and go to its neighbor and continue sending messages. Okay, so you can do this, or you can have more than doubly connected ring to get over the problem of some machines in the ring failing and things like that. So if you have a doubly connected ring, what you need to realize is a message can take at most n over 4 hops to get to its destination in a ring with n nodes. Okay, because you can also always send it on the inner ring, which is going to hop. So it's like a fast path to get to where it needs to go, and once it's reached close to its destination, you send it to the right node. Okay, so it allows you to send messages in fewer hops than a singly connected. Okay, but it's also more expensive to build because you need multiple connections. Each machine is connected to 4 other machines. Okay, so let me do this slide and then I'm going to stop here. This is a different kind of topology which is called a bus-based topology. In a bus-based topology, your network is a shared medium. Okay? All machines are connected to this shared medium, And what this means is because the medium is shared, only one machine can communicate at any given time. Okay, this is like an open environment where if everyone starts talking, then nobody can hear anyone anymore. Okay, so you only need one person to be talking and other machines are all listening. And if whoever is talking is addressing a certain person, they actually hear what is being said and the other people can tune out, but you cannot all talk at the same time. Okay? Same is true here. So in the bus-based network, if two machines try to send packets on the network, they are going to collide because it's a shared medium. Okay, so you can have only one machine talking at any given time. Okay, so here is an example of a linear bus where there is a wire that's common. So you cannot actually send all packets at the same time. They will collide and then garble each other. Okay. Ethernet is an example of a shared medium. If you actually use an Ethernet LAN, that says that if you are connected 10 machines on a switch, only one machine can actually send a packet at any given time. This is traditional Ethernet. You have more sophisticated forms of Ethernet where that's not true. But traditional Ethernet was a shared medium. Okay. So as the number of machines grow, it says that if more than two machines want to communicate at the same time, you basically have to have a way by which you decide which one wins. Because if both of them try to do it, neither of them can actually get their messages across. The messages just collide with each other and garble each other. So this is the cheapest form of a network, which is to use a shared medium, so you don't need actually wires going from one node to another. So both you can have a linear bus or a ring bus. Ring bus is an example of a Wi-Fi network, and what's in the middle is your router, and the links are actually wireless links, so going from nodes to a router. What is shown is a linear bus is essentially a wired Ethernet, where you have actual wires going on the switch, and inside the switch there is a shared medium that allows all packets to go to all networks or all nodes. So that's basically what is more common in LAN environments today. So we have basically looked at a variety of topologies. We're going to stop here today. Next time I'm going to use some of this background to do the next topic, which is remote procedure.